Okay, so these notes are over inverses of relations and functions. So an inverse of relation is the set of ordered pairs obtained by switching the coordinates of each ordered pair in the relation. So basically, x becomes your y and y becomes your x. So here I've got a list of points, and I'm going to plot those points. There it goes. And so I have 0, -3. So 1, 2, 3. I've got 1, -1. Why is that not drawing? There it goes. I've got 2, 1. I've got 3, 3, and 4, 5. 1, 2, 3, 4, 1, 2. Okay, so I just have a bunch of points. Now I'm going to write out what the inverse is. So the inverse, let me use a different color. Let's do this orange. Okay, so the inverse means I'm going to switch the x and the y's. So my points are going to be -3, 0, -1, 1, 1, 2, 3, 3, and 5, 4. Well, if it'll write for me. 5, 4. Okay. All right, so now I'm going to plot the inverse. So -3 zeros here. -1, 1, 1, 2, 3, 3, and then 5, 4, 1, 2. Okay, so the purple is my relation, the orange is my inverse. What's special about the inverse, and you can see it here, I have the imaginary line y equals x graphed. Your inverse will always reflect across the line y equals x. So inverses reflect across y equals x. If it reflects across any other line, then it's not an inverse. Okay, so it has to reflect across that imaginary line y equals x. Okay, so here the notation, we write the inverse of the function as the inverse of f of x, and it looks like f is being raised to the negative first power. That's not what's actually happening. It's just the way that you write the notation inverse. Okay, and functions that undo each other are called inverse functions. So here, function notation is f of x. Inverse notation is the inverse of f of x. So in black, I have graphed f of x equals x squared plus 1. And then in blue, I have the inverse graphed. And I know it's the inverse because it's reflecting across that line y equals x. So you can tell if it's an inverse or not just by looking at the graph. Now, to write the inverse of a function, you're going to follow these steps every single time. So first you're going to write f of x as y. Then you're going to switch your x and y's and then solve for y, and then you'll write it in inverse notation. So here I have f of x equals 3x plus 1. So my first step is I'm going to rewrite f of x to be a y, and I just write it over it. And now I'm going to switch x and y. So I'm going to rewrite this to be x equals 3y plus 1. My next step is I'm going to solve for y. So I want to get y alone. So I'm going to subtract 1. So x minus 1 equals 3y. Now I can divide by 3, and I get that y equals, I'm going to split it up. So I'm going to say it's 1/3 x minus 1/3. And then my last step is I'm going to write it in inverse notation. So my original was f of x, so it's going to be the inverse of f of x equals 1/3 x minus 1/3. And if I were to graph my original function and my inverse function, they will reflect across the line y equals x. I'm going to find the inverse of g of x equals x squared plus 2. So first step, always write over your function notation as a y. So g of x, I'm rewriting it to be a y. And now I'm going to switch my x and y's. So x equals y squared plus 2. And now I'm going to solve for y. So my first step is I'm going to subtract 2. And I get x minus 2 equals y squared. And now to get y alone, I'll square root both sides. So I get that y equals the square root of x minus 2. And my last step is to write it in inverse notation. So my original was g of x, so I'm going to write it as the inverse of g of x equals the square root of x minus 2. I have f of x equals 5x minus 1. So I'm going to write over f of x and make it a y. And now I'm going to switch x and y. So x equals 5y minus 1. So to solve for y, I'm going to add 1. So x plus 1 equals 5y. Now I can divide by 5. So I get that y equals, I'm going to split it up. So I'm going to say it's 1/5 x plus 1/5. And my last step is I'm going to rewrite it in inverse notation. So my original was f of x, so it's going to be the inverse of f of x equals 1/5 x plus 1/5. I've got p of x equals 1/2 times 3 minus 2x. There are several different ways you can approach this one. You can distribute the 1/2, or you can jump straight into multiplying by 2. It doesn't really matter. So first I'm going to rewrite p of x to be a y. I'm going to switch x and y. So x equals 1/2 times 3 minus 2y. So personally, I like multiplying by 2. If I multiply by 2, I'm going to get rid of that fraction. So I have 2x equals 3 minus 2y. And now I can subtract 3. So I get 2x minus 3 equals negative 2y. I can now divide by negative 2. I'm going to do that to everything. So I get that y equals negative x plus 3/2. And my last step is to put it in inverse notation. So my original equation is p of x. So my new function is going to be the inverse of p of x equals negative x plus 3/2. All right, I've got Lm of x equals x plus 2 squared minus 5. So rewrite Lm of x to be a y and switch x and y. So x equals y plus 2 squared minus 5. So I'm going to add 5 to each side. So x plus 5 equals y plus 2 squared. My next step is I'm going to square root both sides. So the left side I have x plus 5 equals, on the right side I just have y plus 2. And my last step to get y alone is I'm going to subtract 2. And when I subtract 2, it's going to stay outside of the radical. So I have y equals the square root of x plus 5 minus 2. And then the very last step is to put it in inverse notation. So my original is Lm of x, so it's going to be the inverse of Lm of x equals the square root of x plus 5 minus 2. All right. And last example, I'm just asking if f of x equals x squared plus 2 and g of x equals negative x squared minus 2, are these inverses? And this answer is no. And the reason why is they are not reflecting across that y equals x. Okay, they're reflecting across the x-axis, but they're not reflecting across that magic line y equals x. So those are not inverses. And that is it for our notes over inverses of relations and functions.